See, I was dreading this, because honestly, I don't want to have to talk about it. I should probably just explain first. Look, in the last video, we talked about polynomial functions, and we kind of scanned over parabolas. We only talked about the different types of equations you could see it in, like its standard form or its vertex form, which showed you all the transformations that could have been done to it. But there's also one last thing that we gotta talk about, and I did kind of mention it in the last video. The focus and directrix of a parabola. Just absolute bull crappery at its finest. It sucks.
Damn.
It sucks. It feels useless to know. See, here's what the regions is gonna do. They're gonna take a giant boot, shove it right up your then they'll be like, alright, here's the focus and directrix. Tell me the equation for the parabola. What parabola? What? It's actually so dumb. But I'm gonna tell y'all how to do it. I'm gonna use the regions question as an example to prove to you it might not be too bad. But let's just start off with talking about the axis of symmetry. Now, the axis of symmetry is the line at which a parabola is symmetrical over. If we look at the graph, x squared is symmetrical over the y-axis, which that can be represented as x equals 0. If you look, it's like a mirror as you go across. If we look at this graph, x squared plus 3x minus 6, the axis of symmetry, it's not so obvious. That's where you need the axis of symmetry formula, negative b divided by 2a. In order to know the a and b values, you need it in standard form, like this right here. You would see the b here is 3, so you'd have negative 3 at the top. And the a here is 1, so you want to put 2 times 1 at the bottom. And the axis of symmetry is where x equals negative 3 over 2. The axis of symmetry is a nice thing to know. I will mention it when we talk about focus and directrix. Let's just move on to it. Let's just get it out the way.
No.
Now we gotta talk about it. What is the focus and directrix? It's a line and point at specific spots to where any point in a parabola is equally far from both.
I don't think you understand!
Let me explain. If we take this random point right here, 2, 1, if you count, it is 1, 2 units away from the directrix, and it is 1, 2 units away from the focus. If you take the turning point, it is 1 away from the directrix and 1 away from the focus. If you take any point on this line, it is equally far from the focus as it is from the directrix.
What?
Now, like I said earlier, when the boot is shoved way up there, they're gonna give you these two things and tell you find the equation for the parabola. And to do that, it is just annoying. But before talking about that, we need to go over 3 things to note about the focus and directrix. First is with the focus. No matter where the focus is, it will always be on the axis of symmetry. Now for this graph right here, we don't need to find it, it's just x equals 0. You can see the focus is on that same line right here. If we had a directrix like this, and a parabola was like, I don't know, maybe like that, then the focus would have to be right somewhere on this line. It would probably be around there for something like this. The second thing you need to remember is with the directrix. The parabola never intercepts the directrix. Notice how this is going up and how it's never going to touch this. For every single parabola, this cannot be touching it. If we had a graph like this and a focus there, the directrix has to be over here. It can't touch it. It can't be like there. And the last thing you need to know about is that the turning point will always be in between the focus and directrix. Because remember, the focus and the turning point has to be on the same line. And also remember, any point in the parabola has to be equally far from both of these. And the only spot on this line that satisfies that is right in between the two. With those 3 things in note, we're now ready to make an equation using only focus and directrix. Now this question I got right here is a regions question, just to show you the type of thing you might see on it. It is a multiple choice, but I ain't giving you that. Given that the directrix is at y equals 0, so it's just the x-axis, and the focus is at negative 3, 2, we need to find the equation for the parabola where any point on it is equally far from both. Now let's tap into our knowledge from earlier. Let's think.
Shut the hell up!
Well, we do know that the turning point focus has to be on the axis of symmetry. The turning point has to be somewhere on this line. We also know we have to find a spot where it's equally far from both. The only spot that makes sense is right here, because it's 1 unit away from the focus and 1 unit away from the directrix.
Let him cook now.
Okay, we got the turning point, but now what? Well, wait. Now remember, the parabola cannot intercept the directrix, meaning it's probably going up here somewhere. So we at least know that whatever equation we got going here is going to be positive, no negative in the front. What are we going to do from here? We kind of know what it's going to look like in general, but that's it. Well, you have to remember, by definition, what is a directrix and focus? Well, it's a point and line where all spots on the parabola are equally far from. That's like my 8th time saying it. So knowing that, for no matter what the x and y value is, they will always be equally distant.
Did you hear that?
We can take the random coordinate x, y, and we can use that to find what we got going on here. We gotta tap in. Remember its definition, it has to be equally far. But how are we supposed to know the distance? There's no numbers. Now x and y could be anything, so there is no number we put here. We actually put in the variable y.
I beg your pardon?
The distance it is from the directrix is y. Now if you don't really understand that, just look at this. This is a random coordinate 4, 2. The x value is obviously 4, but the y value is 2. And if we look at its distance from the x-axis, it is 2 away. See, we can do this because our directrix is exactly on the x-axis, meaning no matter what coordinate we take, the y value of it will always be equal to the distances from the directrix or the x-axis. Now here's the thing I should note, because they could pull you with this. If there's a directrix at like y equals -2, it's not going to be the same. The distance would instead be y plus 2, because you can see it's 2 units away from the x-axis. So you have to use it as kind of like the guidelines. If it's below it, you're going to have to add a value. If it's above, you're going to have to subtract. In this case, it's nice and basic. We don't got to worry about that. So we know that. We know that the distance there has to be y. But that also means the distance here must also equal y. Because remember, it has to be equally distant from both the focus and directrix. Now see, technically, the y distance we can't find. This could be any point. It could be any value. We don't know. So what numbers do we have? It's all just letters. Well, look at the numbers that we do have. We know that the focus is at -3, 2. And so to find its distance from any point on the graph, we have to pull out the distance formula. I've been saying distance a lot. I probably should have mentioned that earlier too, but you need to remember the distance formula for this. See, the distance formula is the square root of x2 minus x1 squared plus y2 minus y1 squared. I forgot if that's provided on the regions. I don't think it is. And so with that in mind, you're gonna have to memorize this. We're trying to find the distance that the focus is from any point on this parabola. If you look here, we know the distance has to equal y, so we want to plug y in for that. And here we obviously need 2 coordinates, the x and y, which represents any coordinate on the parabola, and then -3, 2, because we're trying to find a distance from that. So let's say our x2, y2 is the x and y, and our x1, y1 is -3, 2. We now want to just plug these in to the equation. Now I'm gonna have to clear this area up to get some more space, because this is gonna take a little bit of simplification. Alright, so I cleared up some space here. So the first thing we want to do, we want to get the square root out of here, because we're making an equation here. And in the equation, we have the y alone on one side set equal to x and some random gibberish. And we can see we have a y stuck in here, so we want to try getting that out first. So we're just going to square both sides, which now we have y squared equals all the stuff that was under the radical, which now that we have this, we want to expand these two right here. We have x plus 3 times x plus 3 and y minus 2 times y minus 2, which you can't just like square root both sides and just remove all the squares. That's just not how it works. Because if we have like 4 squared equals 2 squared plus 2 squared, you get 4 equals 2 plus 2, which means 4 equals 4. You're like, oh, there we go, there's equal. But in reality, if you actually square all the things, you get 16 equals 4 plus 4, which actually shows that it's not equal. See how you can get a completely different result if you square root both sides like that? That's because of this plus right here. When there's a plus or minus, you can't be pulling stuff like that. But anyways, now this is exactly why I hate it. Now we gotta multiply both of these sets out, which I didn't go over this in the last video because I felt like it would be unnecessary, but just in case you don't know, this is how you multiply two binomials. So you want to make sure all values multiply each other. So you want to do x times x, gives you x squared. X times that 3 gives you 3x. This 3 times that x, which is another 3x. And this 3 times that 3, which is just a 9. But we want to do the same thing over here, just, you know, great stuff. Which now we have all of this gibberish on the right. Just look at this! From this point on, you want to just combine like terms, obviously. And remember what I said. In an equation, we always have y equal blah blah blah. So we want to have just a singular y left on, preferably the left side. So we would want to subtract y squared on both sides, which luckily enough, these two cancel out. We also want to add 4y on both sides, which now we're going to have 4y over on the left. Gonna have x squared 6x. The x's won't change. I forgot to add the constants. Sorry about that. Let's just do plus 11 over here.
What?
Wait, I'm actually brain dead. It's actually 13. Keeping you on your toes, you know. And lastly, we want a lone y on the left. So we're gonna divide both sides by 4. After all that work, we finally get this. Man, I forgot what we're even doing. Holy cow. Oh yeah, focus on Directrix.
Oh, brother, this guy stinks!
As I'm erasing this, imagine I forgot to press record. I'm not lying to you, I would have quit the channel. Damn. I know I just started it, but I would have quit the channel if that happened. We have the Directrix where y equals 0. We have the focus at -3, 2. Now let's plot the graph. Let's plot the equation that we got here and see if it actually works. So this is the graph we got here, and it seems to fit it pretty well. Turning point at the exact spot we found it at. If we look at this point here, it is 2 away and 2 away. And yeah, that's all I gotta say about focus and Directrix. I'm never dealing with that bullcrap again unless it's on the Regents. And let's go over the last thing, which is the discriminant of the quadratic formula. We all know the classic quadratic formula. It's provided for you on the Regents. X equals -b plus or minus blah blah blah. The discriminant is referring to the root over here, the b squared minus 4ac part, because you can use this to find out a few things about the solutions to a parabola. If you plug in the b, a, and c and you get a value that's greater than 0, then both of your solutions are real, meaning they're going to hit 2 random spots on the x-axis. You're going to be able to see them. Let's take the graph x squared minus 1 for example. We can plug in 1 for the a value, -1 for the c value, and 0 for the b value. And when solving this, you should get positive 4, which is greater than 0, meaning it should have 2 real solutions. It should hit the x-axis at 2 spots, and luckily it does. Now if you plug in the b, a, and c values and it's equal to 0, it's not greater than, it's not less than, then that means you have a double root. We talked about that in the last video. It means the turning point is going to hit the graph. For x squared, we have no b value, we have 1 for a, and we have no c value. When doing all the math, you should get 0, meaning it should have a double root. And it does right here. But see, when you get a value that is less than 0, that means you have imaginary roots. When you graph it, it won't touch the x-axis at all. We can take x squared plus 1 for example. If you plug in the values, then you should get yourself -4. And if you look at the graph, you can see it doesn't touch it at all. How come if you take this little section under the square root, you can all of a sudden just know these things? The square root. That's the problem. Or well, it's not really a problem, but that's the reason. See, when you have a negative under the square root, you're always going to have an I from it. -4 here, if we were to keep going, we obviously know we would get 2i. If you don't know imaginary numbers like that, I don't know what to tell you.
You need to leave.
Meaning, once you keep going, once we finally get our answers, they will have an I in them. When it's equal to 0, you have to look over here. The plus or minus is what causes there to be 2 solutions, because it takes you down 2 separate routes, one where you're adding that value and one where you're subtracting. Now 0 is not positive nor is it negative, it's the in-between point. If you add 0 or if you subtract 0, it'll give you the same thing. That's the reason double roots exist. You're taking 2 different routes, they get the same answer, which is why it's a double root. You count it 2 times and not just once, because you can get it in 2 different ways. And if it's positive, then obviously it's gonna be real, not imaginary. And a plus or minus will send you down 2 different routes and give you 2 different solutions. I don't know why I drew like a weird 6 over there. That's everything about parabolas that should be important on the regents. Don't even bother me about locus definition. That's just a different way of finding the equation of a parabola using Directrix and focus, obviously. It's just more stuff to remember, and you shouldn't be bothering with that. Make sure to like and subscribe. Tell me what you want to hear in the comments, because in the next video I do want to talk about radical functions and leading irrationals. But I'll see y'all then.